Well, hello. Kia ora koutou katoa. Welcome, everybody. Yes, I do speak a little Te Reo Māori, indigenous language of the Māori people of New Zealand. So excited to have you with us today for chapter number 5. Today we are going to be focusing on chemical bonding, but we are going to be focusing instead on the covalent model of bonding rather than the ionic. My name is Joe Lamb, a professor at the University of Cincinnati, and very excited to bring this to you today. So as we always do, we're going to start off with our learning objectives for today. So they're going to look similar to the objectives we looked at with our last chapter with ionic bonding, but obviously covalent bonding works a little bit differently. And what we are going to do today is start the fundamental basis of the next couple of units that we are going to be working with. The big thing I want us to focus on is the Lewis dot structure, the VSEPR theory, and the polarity. Everything that you see here is going to start building upon itself, very similar to a math course, right? You start off with some real basic math, you use the basic math to get into more complicated, complex math. That's exactly what we're going to be doing here. It just isn't going to be math. We're going to be drawing structures utilizing a set of principles, and those principles will help us not only build those Lewis dot structures, but determine things like molecular geometry, polarity, and eventually intermolecular forces. This goes back to that idea, that fundamental idea of this particular course, that structure determines function. How a molecule is built determines exactly how it functions. And so that's the type of stuff that we are going to be focusing on here today. That being said, we are going to list the major differences between covalent and ionic bonding, write Lewis structures, interpret a Lewis dot structure in terms of bonding and non-bonding electrons, understand how single, double, and triple bonds differ, recognize such bonds in Lewis structures, describe the octet rule, use procedures to draw out Lewis dot structures for that and for polyatomic ions, determine the molecular geometry, describe electronegativity, and use it to classify bonds as nonpolar covalent or polar covalent or ionic. Use bond polarity to determine partial positive and negative charges. Given a geometry, determine the polarity, and then name covalently bonded compounds. So lots of things we're going to take care of today. I feel like this is going to be a little bit longer video when compared to that of the ones that we have done previously, but that's just because we have so much material that we need to spend some time and get through. So that being said, I guess we're just going to have to go ahead and get started. And I think one of the best things that we can do to start us off here is to simply differentiate between ionic and covalent compounds. And we can differentiate them between their physical and chemical properties, how they're put together, as well as actually how we name them. Or their nomenclature strategies are very different as well. But let's start off with ionic bonding. Remember and recall that ionic bonding occurs between very dissimilar elements, in particular between a metal and a nonmetal. So when we looked at ionic compounds, primarily we would look at a metal and a nonmetal, such as sodium chloride, calcium chloride, potassium oxide, and so on. Covalent compounds are a little bit different. They are going to occur between similar or identical elements, nonmetal and nonmetal. So we're looking at pretty much everything that's chemically bonded with stuff that's just to the right of the stair step. So we've kind of limited in the number of elements that we can go through and utilize. But I want you to think of covalent or molecular bonding as solely between two nonmetals. That is, two things that are on the right-hand side of the stair step on the periodic table. Metals can bond with other metals through things like alloys. Those are beyond the scope and sequence of this course, so I wouldn't worry about it at this time. Recall that ionic bonding involves the transfer of electrons. Again, it is all about getting that octet rule satisfied. It's all about either getting rid of or gaining electrons in order to get to have 8 electrons in the outermost shell. And covalent bonding is a little bit different. It involves electron sharing. So the goals are still the same here. We're still trying to obtain 8 electrons in its outermost shell, or 2 in some instances. But rather than donating electrons, that is one atom getting rid of its electrons and another atom gaining its electrons, 2 atoms are going to share pairs of electrons in order to satisfy the octet rule. You'll see why that's the case when we look at a couple of examples here in just a little bit. Ionic compounds involved an array of alternating and positive negative ions. If you remember, that goes back to the lattice structure that we've talked about previously, where we have repeating positive and negative ions that maximize attraction and minimize repulsion. There's no discrete molecules. We do have this thing that's called a formula unit, where we take the atoms and we look at the lowest whole number ratio, and that's how we describe it. So NaCl, for example, is not just one Na ion and one Cl ion. It's a repeating array of positive and negative ions, positive sodium ions and negative chloride ions, but we describe it as a formula unit that is in a 1-to-1 ratio, even though there may be millions of atoms, billions of atoms in a single grain of sodium chloride. Covalent bonding occurs in discrete separate molecules, so you don't see the lattice structure that you saw previously. And that plays a huge role in things like boiling point and melting point, because covalent compounds tend to have relatively low boiling points and melting points, and that's because when we melt them, we're not breaking the bonds within the molecules themselves. We're breaking bonds in between separate ones. Those are called intermolecular forces, which are much weaker than the covalent bonds that we find in molecular structures, and weaker than those that we find in ionic structures as well. Ionic compounds tend to be solid at room temperature. Again, think in terms of like sodium chloride. Most salts you're going to find are solid at room temperature. Covalent compounds may be solids, liquids, or gases at room temperature. It depends on a variety of different factors that we'll be looking at. Most of what we will find, though, are liquids and gases at room temperature. Ionic compounds can conduct electricity when dissolved in water, so the ions are in a lattice structure. When they are a solid, they're very close together, but when you put them in water, they dissociate, that is, they break apart into their ions, and those positive and negative ions are what allow for the conduction of electricity in solution. Covalent compounds or molecules cannot conduct electricity when dissolved in water. There's a very common misconception that water in and of itself has the ability to conduct electricity, and that is 100% false. The reason that certain liquids that contain water can conduct electricity is because they have free-flowing ions in it. They have ionic compounds that are dissolved in water, which goes back to the previous point that we just discussed. So, as I mentioned previously, there's just a lot of differences between ionic and covalent compounds. I would say that this slide is probably one of the more important things that you're going to find in this particular unit, because it does provide a very discrete and very straightforward differentiation between the properties of ionic compounds versus the properties of covalent ones. And so if we look at things on a molecular level, I'll go back to the ionic structure that's on the left-hand side of the slide here. We do see that repeating positive and negative ions. We see that lattice structure that is infamous for being parts of the ionic compound. You see that it maximizes attraction and minimizes repulsion in this particular structure. And again, it goes back to the formula unit here. Everything is in a 1-to-1 ratio. I have one negative ion per one positive ion, and so that results in a name being something, well, example, sodium chloride being in a 1-to-1 ratio. It's NaCl. When we look at water on the right-hand side here, we don't see that repeating positive and negative ion structure, but rather what we see are discrete molecules. And those discrete molecules play a huge role in things like melting point, boiling point, and a variety of physical properties that molecular compounds has. So you can see the very discrete difference between what you see on the left-hand side and what you see on the right-hand side here. On the left-hand side, we see that lattice structure of positive and negative ions repeating one another, but on the right-hand side with covalent bonding, we see very discrete molecules. You also see dashed lines that exist. Those dashed lines are representative of what are called intermolecular forces. That are forces that exist between different molecules. They're dashed lines because they're considered weaker than ionic and covalent bonds, which is why they break much easier. So for example, when you melt water, for example, you have H2O on the right-hand side here. When you melt water, or when you melt ice rather, it's still H2O, right? H2O is a solid, is ice, and H2O is a liquid, is water. So when it undergoes a phase change, we're not changing the chemical components that make up H2O, but rather what we're doing is we're breaking the forces in between the different molecules, so basically just separating them further apart, or if we're freezing them, bringing them closer together. So it's a little bit different when we look at melting or dissolving or boiling these types of compounds, because how they break apart is very different than how ionic compounds break apart. So what exactly is a covalent bond? Well, a covalent bond is the result of two nuclei sharing electrons. And the whole goal of this, can we go back to what we talked about with ionic bonding? The whole goal of this is to satisfy the number of outer shell electrons that make it the most stable. We go back to that octet rule. Most of the time this is 8, sometimes it is 2. So if I take a look at two hydrogen atoms that are here, hydrogen wants to satisfy what's called the duet rule, which is a little bit different than the octet rule. That is, hydrogen wants to have 2 electrons in its outer shell, not 8. Well, if one hydrogen donated an electron to another, one of the hydrogens would have 2, but the other would have 0. So one would have the duet rule satisfied, but the other would not. So what ends up happening is that one hydrogen atom shares its electron with the other, and vice versa. The other hydrogen shares it with the original hydrogen. Things share in pairs. So what you end up with is a shared pair of electrons that exist between the two hydrogens. This results in the duet rule being satisfied for both hydrogens because both hydrogens claim both of those electrons because they're shared in between them. And this results in a chemical bond that is being formed, a covalent bond, and you end up with a hydrogen molecule, which you see there as H2. So really it's these types of strategies, this type of sharing of electrons between different atoms that are going to result in these covalent bonds being formed. So as I mentioned before, it's a little bit different than ionic bonding, but hopefully as you see the sharing of electrons over the course of time, you'll understand how this idea works. So the concept of the Lewis structure. Lewis structures are designed to help us visually show the electron sharing associated with covalent bonding. It shows the number of electrons that are shared, it shows how those electrons are being shared, and it plays a really huge role in determining how many electrons are shared in between different chemicals and how those bonds are being formed. I know I've said it multiple times, but I'm trying to get the point across here. So let's consider fluorine. Fluorine has 7 valence electrons in its outer shell, and it only needs 1 valence electron to satisfy the octet rule. And then let's consider hydrogen. Hydrogen has only 1 valence electron and only needs 1 for a full outer shell, so the donation of electrons between one and the other doesn't really make a whole lot of sense. Hydrogen, if it donated its electron to fluorine, would result in fluorine having a full outer shell, but hydrogen having no valence electrons. If fluorine were to donate its electron to hydrogen, hydrogen would have a full outer shell because it would have 2 valence electrons, but the fluorine would only have 6. So it doesn't make much sense to donate electrons in this situation because there really isn't a way where all of the duet and octet rules have the ability to be satisfied. So what we do is we share, and you can see this between a variety of different atoms on the right-hand side here. Hydrogen and fluorine are going to share a pair of electrons. So you see the electrons that exist between the H and the F, once the sharing has occurred, those are a shared pair of electrons that represent a covalent bond. You could say the same for fluorine and fluorine, and bromine and fluorine. Each of those atoms has 7 valence electrons in its outer shell. So a donation of electrons from one to another really doesn't make a whole lot of sense in regards to satisfying the octet rule for both atoms. However, if each one shared an electron with each other, well, then what you end up with is a shared pair of electrons between them. The octet rule is satisfied for both fluorines, or bromine and fluorine if you look at the bottom pair. And thus, you have a covalent bond that forms in between them. So it really depends on the situation, and it will also depend on the situation on how many electrons are shared. And we'll talk more about multiple covalent bonds here in just a moment. But as you see, the shared pair of electrons are known as bonding electrons, and I know previously it showed them as a pair of dots that were in between the two atoms that were present, and some books, some people will show it that way, but I don't like that. I really like to be able to differentiate between the individual electrons that are on the outside of the atom. We'll talk about lone electrons in just a moment, but also to differentiate them between the shared electrons. The line in the middle represents a shared pair of electrons, so I ask that you please show these as lines. I hate the shared dot pictures. I get the point to show the shared pair, but it's frustrating. There are better ways to do this. Seriously, please just draw a line. Okay, please just draw the line. It will make your life easier. It will make my life easier. It will make me happy. It will make other professors happy. I don't care what they say. My way is the right way, and you can fight me about that. Anyways, non-bonding electrons are pairs of valence electrons that are not involved in the electron sharing process. So these are what are referred to, sometimes they're referred to as lone pair electrons. I'll probably refer to them more often as lone pair electrons because that's just what I'm familiar with. But if we look at each of the following structures, we can see that the dots that are not in between the two atoms, or dots that are not in a line rather, are considered to be lone pair or non-bonding electrons. So if we take a moment, let's think about how many do we see in each of the following structures. On the left molecule here, the H2, we have a pair of bonding electrons but no non-bonding or lone electrons. In HF, we have a pair of bonding electrons between the H and the F, and we have 6 non-bonding electrons located on the fluorine. Between F and BR and F, we have a pair of bonding electrons each, but each has a total of 12 non-bonding electrons on the outside of it. So fairly easy to go through and count those, but again, just as always, practice, practice, practice. Now, as we mentioned before, covalent bonding can involve the sharing of electrons, but it can involve the sharing of more than one pair of electrons, and we refer to these types of bonds as either single, double, or triple bonded. Single bonds involve the sharing of a single pair of electrons. Double bonds involve the sharing of 2 pairs of electrons, and triple bonds involve the sharing of 3 pairs of electrons. Now, Determining whether it shares 1, 2, or 3 pairs is dependent upon a couple of different factors. It depends on what atoms you're looking at. It depends on how many electrons need to be shared in order to satisfy the octet rule. So there's quite a few things that we need to consider before we go through and try to determine how many electrons are being shared. We'll talk about that process in a moment. And explicitly understanding that bonding electrons and non-bonding electrons occurring in pairs is something that's quite important. Now, do we see Lewis structures and compounds that have rogue single electrons available? Yes. In fact, there was actually one of those on the AP exam this past year that threw some of my students for a little bit of a loop, but for the most part, they actually figured it out quite well. But I just ended up with really good kids, and I feel like I do a good job. But that being said, this helps us with counting electrons when we look at Lewis structures, because we're going to end up with pairs of electrons. So electrons will occur in even numbers as we go through and do this process. Knowledge of bonding and atoms themselves and the tendencies of how atoms bond helps to eliminate mistakes. So let's consider nitrogen. Nitrogen has 5 valence electrons in its outer shell in its normal state when it exists as just an atom. It needs 3 more to have a full outer shell. So what you end up finding is that nitrogen tends to form 3 bonds, right? If it shares 3 electrons, it gets 3 electrons in return. So as a result, it would end up having 8 electrons in its outer shell. So we find that nitrogen tends to form 3 bonds. We consider oxygen. Oxygen has 6 valence electrons. It needs 2 more to have an outer shell, so it typically forms 2 bonds. And carbon has 4 valence electrons. It needs 4 to have a full outer shell, so it will typically form 4 bonds. So this is known as the NOC rule. NOC means nitrogen, oxygen, and carbon. I'll be perfectly honest with you. The first time I heard this was when I taught at UC. Never heard of that before, but some professors swear by the NOC rule. So, more power to them as they go through and help you guys through this. But it does help with tendencies. Is this always the case? Not necessarily. There are many instances in when the NOC rule does not necessarily apply. But again, understanding periodic trends and periodic tendencies does help us to understand how many bonds these things typically will form. So let's do a quick review and quick check. I'll give you a few moments to look over some of these questions here. The first question here, I just want you to know which of the following would you expect to have covalent bonding? Again, think about what we've talked about previously in terms of ionic bonding versus covalent bonding, metals and nonmetals versus all nonmetals. And then I want to know which of the following is inaccurate about the line represented by the molecule HF here. So take a few moments, we'll come back and we will discuss it in just a moment. All right, so looking at the first question here, it says, which of the following would you expect to have covalent bonding? Remember that covalent bonding exists between 2 non-metals. So I would expect HBr to be what is covalently bonded here. And then it also asks which of the following is inaccurate about the line represented. And the first statement there says it represents 2 shared electrons. Well, remember, lines in between atoms represent 2 electrons that are shared between them, which also represents covalent bonds. So A and B are accurate. Representing non-bonding electrons, well, those would be the dots that are on the outside. The line does not represent non-bonding electrons. It represents bonded electrons. So the incorrect answer there is C. It represents non-bonding electrons. I'd also like you to take a moment here and determine the number of bonded electrons and non-bonded electrons in the following Lewis structures and designate the bonds as being either single, double, or triple bonds. So again, look at the number of lines that are present there. Remember that each line represents a pair of electrons, and we will come back and talk about them in just a moment. All right, so if I'm looking at the very first question here, it wants to know how many bonded electrons and non-bonded electrons are here. So let's count them up. So I'm just going to count up the number of lines. So 1, 2, 3, 4, 5. There's 5 lines. 5 lines represents 10 electrons. Remember, each line represents a pair. So there's 10 bonded electrons in that first one, and I see no dots on the outside, so no lone pairs. So there would be no non-bonded electrons. The next one over, I look at HCN, count up the number of bonds, 1, 2, 3, 4. So each bond represents, again, 2 bonded electrons, so multiply by 2, so that's a total of 8 bonded electrons. You have a non-bonded pair on nitrogen, so 2 non-bonded electrons. And then CO2, very similar. I have 1, 2, 3, 4 lines. Each represents a pair of bonded electrons, so that results in 8 bonded electrons. And then I have 8 dots on the outside of both of those oxygens combined, so 8 non-bonded electrons. So very easy. Go through, count the number of lines, multiply by 2, and just count the dots on the outside. That will tell you the number of bonded and non-bonded electrons that are present in each of these individual compounds. Okay. So what I'm going to do now is something a little bit different. I deviate from many textbooks when I go through and draw out Lewis dot structures. And the reason I do it this way is because it eliminates so many exceptions to the rule, I guess would be maybe the best way to describe it. I've come up with a set of rules to help you draw out your Lewis dot structures. And I promise you that if you draw them this way, you follow the steps, you end up being less error prone. You don't make mistakes if you follow these steps. And it's one of the biggest things I can promise you is just this way is going to make your life a whole lot easier. I can 100% promise you that. You just have to follow the steps, work through them. This is something we're going to do together. I'm going to present the steps. And I want you to write them down. I really want you to take in what these steps are, because this is a systematic approach, a very systematic procedural way to draw out your Lewis dot structures and to draw them out correctly. And even if you're in a course that is beyond this, let's say you're in a 1040 course, you're in a general chemistry course, and you have things that go beyond the octet rule, you can still apply these rules to it. There's just a little bit at the end that we end up adding to it. So if you want to see more of that, go check out one of my Chemistry 2 or my AP Chemistry videos, because it walks through it a little bit more detail than what I do here. We don't do anything with exceptions to octet rules here in this 1030 course. So that being said, follow these steps and you will draw Lewis structures. Remember, we're drawing Lewis structures for compounds. We've done this for atoms before, but drawing them for compounds is going to require something a little bit different, okay? Step 1, determine the type and number of atoms from the formula. Break down the chemical formula you have, write out the number of atoms and each atom that's present. So if you're looking at a chemical compound with H2O, write out the fact that you have 2 H's and 1 oxygen. Determine the total number of valence electrons. Remember that is information that is based off of the element's location on the periodic table. So if I look at a periodic table, I should be able to determine the number of valence electrons in individual atoms, and then I can step by step determine the total number of valence electrons I need. This essentially tells you roughly how many electrons need to be in your structure when you are done. So step 3 is determine the central atom. This is the atom that is furthest away from fluorine but not hydrogen. Okay? I'll repeat that. Determine the central atom. It is the furthest away from fluorine or not hydrogen, or if you're familiar with the concept of electronegativity, it is the least electronegative atom that is present in the compound that is not hydrogen. If your molecule has just 2 atoms, there really is no central atom, because 2 atoms are just going to bond together. It doesn't tell you how the atoms bond together because it doesn't need to, right? 2 atoms are just going to bond together. Step 4. Bond your other atoms to your central atom with single bonds. So figure out what your central atom is and bond everything. Take one line and put it in between each atom that you're going to surround the central atom with, and draw a line in between those atoms and your central atom. The next step, step 5, is to add pairs of valence electrons or lone electrons or non-bonded electrons, depending upon your nomenclature, to all atoms to reach the octet rule. You may end up going beyond the number of electrons in step 2. That is okay. Okay, I cannot stress that enough. You may end up adding more dots than what you find in step 2. That's fine. We can change that as we work through it. Read step 6. If the number of electrons in the structure is equal to the number of valence electrons, it is done. So if in step number 5, you add up the total number of electrons in the structure and it's the same as what you have in step 2, you're finished. You've drawn the correct structure. If not, you need to remove 2 lone pairs of electrons and create multiple bonds until the number of electrons in your structure and valence electrons is the same. And keep in mind that halogens, that is those things in group 17, fluorine, chlorine, bromine, etc., and hydrogen can only form 1 bond. So there's a set of rules you work through. If you end up building your structure and you have more electrons than are necessary, more electrons than you need in step number 2, what you're going to do is you're going to remove pairs of electrons and add lines in between them. What that does is that reduces the total number of electrons in the structure, but it maintains the octet rule, so you don't have to worry about going back and making sure, oh, everything has 8. This systematic approach, these 6 steps, will work for nearly every single Lewis dot structure that you will draw in this class. I promise you that. So what we're going to do now, and what I'm going to do is I'm going to switch over to my iPad and I'm going to show you how to apply the steps for each of these 6. It's going to take a little bit of time. It takes a little bit of practice, but as we do this, notice how I follow the individual steps. I'll be back with you in just a moment. All right, so as I mentioned before, all we need to do with each of these is just go through and follow the steps. So we'll do this one step at a time for each of these 6, and then we'll take a look at some more. Just again, it's all about practice with this. If you follow the steps, you'll do just fine. So I'm going to follow the steps. So step number 1 is determine the number of atoms of each. So I have 1 nitrogen and 3 chlorines that are based off of that chemical formula. Next step is to determine the total number of valence electrons that are present. So again, that is periodic table based. If I look at nitrogen on the periodic table, I find that there are 5 valence electrons for each atom of nitrogen. There's 7 for each of chlorine, but there's 3 of them. So that ends up with a total of 21 here. So we're just going to add those together. So I have 26 electrons to play with as I build my Lewis dot structure. So those are the first couple of steps. The next step is determine your central atom. Remember, that is the atom that is furthest away from fluorine, that is not hydrogen, or the least electronegative atom, if you're familiar with that. We'll talk about electronegativity later on. So here, we're going to use nitrogen as our central atom. And I guess it is good to note that your central atom a lot of times is just going to be the first element that is listed in your chemical formula. Not always, but sometimes for the most part it is. Again, just depends on the formula you're looking at here, but we're going to start with nitrogen as our central atom. We're going to connect 3 chlorines to our central atom, and we're going to connect them all with single bonds. All right, now the next step is to add lone pair electrons or valence electrons in order to satisfy the octet rule. So we need to look at the bonds that are connected to each of these and how many electrons they need in order to achieve 8. So if I take a look at, for example, chlorine, this chlorine here has 1 bond that is attached to it. So that means it already has 2 electrons attached. It needs to have 8, so what we're going to do is we're going to add 6 electrons on the outside of it. And what you'll notice is that it is the same for each chlorine that is around the central atom. The same sets of rules apply. So we're going to add 6 dots to make sure that it has a total of 8 electrons in its outer shell. If I look at nitrogen, nitrogen already has 3 bonds that are attached to it, so that's a total of 6. So in order to get 8 electrons, I need to add 2 more lone dots to its structure. So we're going to add 2 dots there on nitrogen. Now what I need to do is I need to add up the total number of electrons and see if it's 26. So I'm going to start with the bottom left chlorine. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So there's 26 electrons in my structure. That matches the 26 electrons I had originally. I'm done. That's exactly how you go through and draw that Lewis dot structure. So that is the correct structure for NCl3. Let's continue moving on. We're going to scroll down here. Let's do pH3. And again, we're going to follow the exact same steps that we did in our last Lewis dot structure. So first thing here, I have 1 phosphorus and 3 hydrogens. Phosphorus provides me with 5 valence electrons. Again, that's periodic table location based. Each hydrogen is 1, so that's 3. So I have a total of 8 valence electrons to play with here. Phosphorus will be my central atom. Again, it is the furthest away from fluorine. That is not hydrogen. Can't be hydrogen, so it has to be phosphorus here. We're going to attach each hydrogen with a single bond. All right, now remember, when we do this, the next step is to add lone pairs to satisfy the octet rule. Remember that hydrogen is different. Hydrogen only wants 2 electrons in its outermost shell. So for each hydrogen that's here, a bond is already attached. Remember that a bond represents 2 valence electrons. So the octet rules are already satisfied for all of the hydrogens. If I look at phosphorus, phosphorus wants to have 8. If I look at the structure here, it already has 6 electrons attached. In order to have 8, we need to add 2 in order to make that happen. Okay? The numbers that are here, and I should bring this up as well. The numbers that are here, do not bring those over when you count over the number of valence electrons in the structure, okay? Because the number of valence electrons that are present on each atom can shift within the Lewis structure. So don't always anticipate that it's going to have 5 things attached to it. You have to take into consideration the octet rule. So follow the rules as they are given. Ignore the numbers that I just circled or squared until you go back and recount. So as I do this, I count them up again, 2, 4, 6, 8. I have a total of 8 electrons in my structure. This is done, okay? So again, notice I don't worry about the 5. I don't worry about the 3. I don't think about those things. I just focus solely on the number of valence electrons that are in the structure. I go back and I recount, okay? Let's do one more here. Actually, we'll do a couple more. CCl3F. Again, same procedure here. So step 1, we have carbon, we have 3 chlorines, and a fluorine. So 4, 21, and 7. Again, look at your periodic table and figure out how many valence electrons there are based on that periodic table location. Each carbon has 4, each chlorine has 7, times 3 is 21, and fluorine has 7 as well. So when I add these up, 32 electrons to play with in my structure. Carbon will be my central atom as it is furthest away from fluorine, not hydrogen. Attach everything to your central atom. For this, it does not matter where you put the chlorines and fluorines. So the fluorine could be on the right side, I really wouldn't care. All right, so now what we need to do is, again, add lone pair to satisfy the octet rule. Don't worry about these numbers. We're solely focused on how many electrons are in the structure and how many more we need to add to get to the octet rule. Fluorine, again, everything wants 8. Fluorine has 2 attached, so we're going to add 6 dots to get to 8. And it's going to be the same for each chlorine. If you look at carbon, carbon already has 4 bonds attached. 4 bonds implies that there are 8 electrons already attached, so we add nothing to our carbon. And now let's add them up and see what we get. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32 in that structure. That is done, and that is a correct Lewis structure. Again, I'm following the exact same set of rules that we just went through and discussed. All right, let's look at a couple of more practice problems here. So HCN. Sorry, somebody's driving by with a very, very large motor. So, good for them. HCN, same steps here. Step 1. So you have an H, C, and an N. 1 valence electron, 4, and 5. For a total of 10 electrons in our structure. We're then going to find our central atom. Our central atom here is carbon. Attach everything with single bonds to your central atom. All right, now we follow the same set of rules. We had lone pair to satisfy the octet rule. Hydrogen here, we don't need to add anything to. It already has 2 electrons. Remember, hydrogen is different, only wants 2 electrons in its outer shell, so it's good. Carbon here has 2 bonds that are attached, meaning that there are 4 electrons already attached. It wants to have 8, so we add 4 dots. And nitrogen here already has 2 attached. It wants 8. We add 6 dots. Remember, when we do this step, we can have more than 10. We'll work its way back down to 10. So don't let this limit the number of dots you add in that next step. Okay? Now, count them up. 2, 4, 6, 8, 10, 12, 14. We have 14 in our structure. That's too many. So what we're going to do here is we're going to take away 2 lone pair and put a bond in between where we removed the 2 lone pair. Since we can only remove them between carbon and nitrogen, we're going to do that. So I'm going to take away that. There we go. And I'm going to add another bond in between them. Sorry, technical difficulties. There we go. So what you'll notice what this does is it keeps the octet rule satisfied. So if I look at the number of electrons that are attached to carbon, 2, 4, 6, 8, and the number attached to nitrogen, 2, 4, 6, 8, octet rule is still satisfied. But what it does is it reduces the total number of electrons in my structure by 2. So now when we recount 2, 4, 6, 8, 10, 12, I have 2 fewer electrons. Now that's still not 10. So we keep doing this process until we have the correct number of electrons in our structure. So I'm going to take away these 2. Take away those 2. Rewrite that. Okay. Struggling here. I'll figure it out one day, folks. Okay. So again, octet rule still satisfied, but now we have 2, 4, 6, 8, 10 in our structure, so it's done. Again, the steps are simple to follow. Okay? It takes a little bit of time to get used to writing these structures and practicing, but over time you kind of get the idea. It's the same steps every time we do this. Let's do 2 more. CO2, same steps. So carbon, 2 oxygens. Each carbon has 4 valence electrons. Each oxygen is 6 times 2 is 12. So I need 16 electrons in my structure. I make carbon my central atom and single bond everything to my central atom. We now add lone pairs to satisfy the octet rule. Again, octet rule, everything wants to have 8. So we need to make sure that everything has 8 in its outer shell. Each oxygen only has 2 electrons attached. So we're going to add 6 dots. The process is the same for both oxygens. And for carbon, as we see here, we have 4 electrons already attached. So we need to add another 4. So again, we follow that step here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So 20 electrons in my structure is too many. We need 16 in our structure. So follow the rules we just talked about. Take away 2 lone pairs, 1 from each atom, and then add a double bond in between them. So all right, and if we go through and redo that, we find that we have 18 in our structure, still too many. I want you to keep in mind that when you go through this process, molecules like to be symmetrical. And so if we have a choice between where we're removing valence electrons, we want to try to keep this molecule as symmetrical as possible. Just atoms tend to like to be that way. They're more stable, if you will. So we're going to add two more, or take away two more lone pair. And add another bond here. And so we end up with 16 in our structure. So there you go. All my octet rules are satisfied. We have 16 electrons in our structure. We are good. Let's do one more practice problem, and then we will move on. Last one here we're looking at is water. Follow the same steps. So 2 hydrogens and an oxygen. So 2 valence electrons, 1 for each hydrogen, and 6. So for a total of 8. Follow the same steps we did before. Oxygen will be our central atom. We're going to attach hydrogens to them. Remember, the hydrogens follow the duet rule. They only want 2 electrons in their outer shell, so by having a bond attached to them, they're already good. Oxygen, however, because it has 2 bonds attached, has 4 electrons on it, wants to have 8. Add 2 more lone pair. So 2, 4, 6, 8. And our structure is now complete. So what you'll find is that it just repeats itself. Follow those steps. It is a very formulaic process. The more you practice with it, the better you get with it, okay? Few more practice problems coming up. We're going to mix in the ionic and covalent Lewis dot structures that we've talked about. And then once we've done that, we'll continue to move forward. But this is one of the most fundamental processes you're going to learn in here, because this builds on itself. Doing this correctly leads to correct geometries, which leads to correct polarities, which leads to correct intermolecular forces. So making sure that we build all of these molecules correctly is super, super important moving forward. I'll bring you back in just a moment. All right, so I just wanted to give you a couple of mixed practice problems as we continue to move forward. So the first one here says potassium iodide. And I know you've been doing Lewis dot structures for covalent compounds, but it is important to be able to differentiate between how you do Lewis dot structures for ionic compounds as well as covalent compounds. Potassium iodide's chemical formula is Ki, meaning that it is a metal plus a nonmetal. And so as a result, we're going to draw our Lewis dot structure a little bit differently. Remember, K has 1 dot in its Lewis dot structure, and iodine has 7. So the transfer of electrons is going to be a little bit different. We are going to be donating electrons versus sharing them. So again, please make sure that you understand there's a difference between how we do ionic compounds, like what we have here, versus covalent compounds. So in this instance, that potassium is going to donate its electron to the iodine, and so our Lewis structure is going to look like this. Okay, so again, that's different than the rules that we set forth previously. Now, this is something that we have talked about in our previous chapter. We've talked about how we go through and draw out Lewis dot structures for ionic compounds. All right, the next one we're going to look at here is CH2O. Again, follow the same set of rules we did previously. This is a covalent compound because we have all nonmetals, so we are going to follow the Lewis dot structures that we discussed previously in this video. So start off with carbon. We have 2 hydrogens and an oxygen. So we have 4 electrons. 2 hydrogens, 1 valence electron each, so that's 2. And each oxygen has 6. So we need a total of 12 electrons in our structure. We're going to start with carbon as our central atom. It is the one that is furthest from fluorine, that is not hydrogen. And we're going to single bond everything to our central atom. Remember, we add lone pairs to satisfy the octet rule. Everything in this molecule wants to have 8 valence electrons except for hydrogen, which wants 2. So each hydrogen is good because it has 1 bond attached. Oxygen has 2 electrons attached because it has a bond attached to it, so we need to add 6 dots. And the carbon here has 3 bonds attached. That's a total of 6 electrons, so we're just going to add 2 here. Count them up and see if we get 12. So 2, 4, 6, 8, 10, 12, 14. So that's too many. So again, just like what we've talked about previously, we take away 2 lone pair. Here we go. Getting better at it. And add another bond. And when you count them up again, you get a total of 12, and our structure is done. So again, just follow those systematic steps as we go through and build our Lewis dot structures. Our last one here on this side is N2. So again, follow the same steps. This is a covalent compound, again, all nonmetals. So we have 2 nitrogens. That's a total of 10 electrons because each nitrogen has 5 valence electrons in its structure. It's just 2 atoms, so there really is no central atom. We just kind of bond it to itself. And again, add lone pair to satisfy the octet rules. Each nitrogen is currently sharing a pair of electrons, so that's 2. Each nitrogen wants to have 8, so we just add 6 dots. and add them up. So 2, 4, 6, 8, 10, 12, 14. So we have too many electrons. So what we do is we just remove pairs and add a bond in between them. Again, that retains the same number of valence, retains the octet rule, but reduces the total number of valence electrons by 2. We recount it up, we get 12. That's still too many, so we're going to have to do this process one more time. There you go. 2, 4, 6, 8, 10. All my octet rules are satisfied. There's a triple bond between those nitrogens. Simple enough. All right. So what we have here is chromium 3 oxide. Okay. So again, a little bit different here. This is an ionic compound. If I go through and do a little bit of nomenclature, I can write out the structure here. So chromium 3, so chromium Cr. Remember that the Roman numeral tells you the charge is 3+. Oxide, oxygen is a 2-, so cross and drop. So that ends up being Cr2O3. So rather than having to go through and show the transfer of electrons, I can actually just write this out as is, because I know that I'm going to have 2 chromiums, each with a 3+ charge. And I know that I'm going to have 3 oxygens, each with a 2- charge, and a full outer shell. Just like that. Again, the difference between ionic and covalent bonding definitely shows when you go through and write out those Lewis dot structures. PF3 and CCl4 are the only ones that are left. So PF3, so phosphorus, 3 fluorines. Phosphorus is 5 valence electrons. Fluorine is 7 times 3 is 21. So 26 total valence electrons in your structure. Phosphorus is your central atom. It's the furthest from fluorine because fluorine's your only other option here. We add lone pair to satisfy the octet rules. Again, everything wants 8. Each bond represents a pair. So each fluorine is going to want 6 because it already has 2 electrons attached. And phosphorus wants a single pair because it already has 3 bonds, which is a total of 6 electrons attached. So now what we do is we go through and we count them up and we end up with a total of 26. And we're done. Again, that systematic process, it works so well. You just have to make sure you follow the steps. But notice I'm not deviating from anything that I've done previously. I'm following the exact same steps that I've done previously. 4 valence electrons in carbon, 7 in chlorine, times 4 is 28, so 32 in our structure. Carbon's your central atom. Attach everything to your central atom and add lone pair to satisfy octet rule. Count up, you get 32. I can't make it any easier, guys. Okay? So take your time. Practice, get good with it, okay? And then that will help you as we continue to move on with some of the more complicated things. Because remember, as I mentioned before, this unit builds. So knowing how to do this is very essential for us to be able to do other things that we're going to do here in just a moment. So as we continue the process of building Lewis dot diagrams, something we also need to consider are what are known as polyatomic ions. And polyatomic ions are built and designed the exact same way. We follow the exact same steps that we've done previously. Figure out how many valence electrons you have, number of atoms, count them up, get the total number of valence electrons in the structure. Figure out your central atom, attach everything to your central atom with single bonds, add lone pair to satisfy your octet rules, and then reduce if necessary. The only difference, though, is that we need to take into account the charge of the ion when we count up the total number of electrons in the structure. So if we consider something like NO3-, if I were to count up the total number of valence electrons just using the elements that make up NO3-, I end up with a total of 23. And if you remember, we talked about electrons occur in pairs. Well, it doesn't make much sense to have an odd number because the electrons occur in pairs. Odd numbers, it's not a pair. So we need to take a look at the charges that are there. A 1- charge indicates an additional electron. So rather than 23, we have 24 electrons in the structure. And then lastly, because it is an ion, very similar to how we do ionic bonding, we put brackets around the ion and put the charge on the outside. So very similar rules apply. The only thing we need to take into consideration is the actual charge of the ion itself. Taking into consideration, we either add or remove electrons in order to get the correct number of electrons in your structure. So for example, if it were a positive charge indicates that we have fewer electrons. So you're going to subtract an electron or 2 from the total number that you have here. And it is based off of the numerical value of the charge as well. So something that is a 2- charge, you're going to add 2 electrons to. A 3- charge, you're going to add 3, and so on. So let's go through and do some practice problems with these, and we'll be with you right now. So you can see that these are the polyatomic ions that I want you to draw Lewis dot diagrams for. We'll do them together here in just a moment, but try them and practice and see what you come up with, and we'll be back in a moment. All right, so let's rock these just like we did the other one. So SO4, 2 minus. So I'm just going to leave this kind of in big screen mode here. Hopefully there's plenty of room to write. I guess we'll find out. We have a sulfur, and we have 4 oxygens. Oh, that's much nicer. Yeah, there we go. So we end up with 6 for sulfur, 4 oxygens. Oxygen is 6 as well, so 24. So that is 30. But there's a 2 minus charge that's here. So we're going to add 2 more electrons to it. So that means that we have 32 in our structure. And now everything else is pretty much just the same. We get our central atom, sulfur, single bond everything to our central atom. Add lone pairs to satisfy octet rules. So 6 on each oxygen. Sulfur doesn't need anything. And when you count them up, you get a total of 32. The only thing we need to do is put that in brackets and put a charge on the outside. So there you go. Now, if you're taking 1040, this Lewis structure is actually going to look a little bit different, and that has to do with the fact that this Lewis structure actually does violate the octet rule. There's something that is known as formal charge. So if you're interested in that, I do have an AP video that does cover that because it does make this structure look just a little bit different. Okay? So NH4 plus, so we have nitrogen, 4 hydrogens. So nitrogen is 5 valence electrons, 4 hydrogens is 4, so that's a total of 9. It does have a positive charge here, so we're actually going to remove an electron, so we end up with 8 total in our structure. And now we build it just like what we've talked about previously. You attach everything to your central atom with single bonds, and you go through it, you find that all your octet rules are satisfied, so we also have 8 in our structure, so we're good. PO4 3 minus, again, this is another one where formal charge would be violated if we were to look at this from a more advanced chemistry perspective, but we're trying to keep it simple for this course. So phosphorus is 5, 4 oxygens is a total of 24, so that's 29, but we have a 3 minus charge, so we add 3 electrons to it, so it means we need 32 in our structure. And again, exact same steps we've done previously. Sorry, I'm a little low on room, and I'm using a stylus that is not optimal, to say the least, but it does showcase the point. So again, the polyatomic ion Lewis dot structure is very similar to the Lewis dot structures we've looked at previously, okay? So we're going to look at the next step of this, which is how does the structure of this determine its shape in 3-dimensional space? I'll bring that to you here in a moment. One of the benefits of Lewis dot structures is it helps us determine the shape of the molecule. And remember that structure determines function. That is, the shape of the molecule in and of itself helps determine its function inside the body or its interaction with other molecules. And how we determine the shape is through the process of determining its molecular geometry. That is, the description of the 3-dimensional arrangement of atoms within a molecule. And the way we do this is through what is called VSEPR Theory, which stands for valence shell electron pair repulsion. And it's simply a set of rules that helps us determine the molecular geometry of a molecule. And so you can think of atoms and electrons as having a very strong negative charge on the outside, right? Electrons are going to be negatively charged. Atoms are going to have negative charges on the outside of them. So things with similar charges are going to want to repel one another, right? They're going to want to push each other apart as much as possible. And so this helps us understand how molecules take shape in 3-dimensional spaces. So for example, if we had 2 electron pairs attached to a central atom, they'll repel 180 degrees. Electron pairs can be considered lone pairs or atoms. So we need to take that into consideration. Sometimes we'll refer to this as the steric number. It's just simply the atoms and lone pairs combined together. So 2 electron pairs would be considered 2 atoms, or 2 lone pairs, or an atom and a lone pair. It's atoms plus lone pairs added together. 3 electron pairs attached to a central atom will repel each other 120 degrees. And that is known as trigonal planar. Trigonal meaning like a triangle, and planar meaning flat, as in it's in 2-dimensional space. 4 electron pairs will repel each other 109 degrees. Now this is different because a lot of people will think, well, 4 electron pairs, it ends up forming a square and you end up with 90 degrees. But we have to remember that molecules exist in 3-dimensional spaces. So we have to take that into consideration when we determine how far apart these atoms or molecules or electrons are going to want to repel one another. So instead of 90, it can actually repel each other more in 3-dimensional space, which is why you end up with 109 degrees. So again, our goal here is to figure out what the geometries are and how we determine their angles. So one thing we're going to discuss here is the concept of group, the concept of steric number. All right. And so what we do is we look at the central atom. In this case, we look at carbon for both of them, and we simply count up the number of atoms and lone pairs that are attached to that central atom. I'm not talking about bonds, but atoms and lone pairs, and that determines what's called the steric number or the group number or the electron pair number. There's a variety of different ways that people use to describe it. And in this instance, we have 2 atoms and no lone pairs. So the angle here is going to be 180 degrees, and this molecule is going to form a linear shape. All right? So again, 2 groups with 2 atoms and no lone pairs. There's really no other way we can look at 2 groups. You can't have an atom and a lone pair. It doesn't quite work that way. In addition to that, I probably should bring this up now as well, is that if you just have 2 atoms in a compound, that is something like N2 or HCl, 2 atoms can only bond in a straight line. So if you just have 2 atoms in your compound, the molecule has to be linear in terms of its geometry as well. So let's say we have 3 groups here. Well, there's a couple of ways that we can interpret 3 groups. We can have 3 atoms and no lone pairs. As you see on the left-hand side here, that results in the molecule being trigonal planar. That is, it has a 120-degree bond angle. You can also have 2 atoms and 1 lone pair. So notice that the molecule on the right-hand side only has 2 atoms that are attached, but also has a lone pair. Remember, that number, that steric number, that electron pair number, that group number, it's the number of atoms plus lone pairs attached to that central atom. So both of these have 3 of them. We just call the one on the right a little bit different because the non-bonding electron pair, that lone pair of electrons, we don't really take that into consideration when we look at the geometry of the molecule as a whole. It plays a role in the shape, but we call it something different. We don't call it trigonal planar because there aren't 3 atoms attached. So what we do call it is we call it bent. If you were to take your hand and put it over the non-bonding pair on the right-hand side, you would see that the molecule looks, well, bent. And for this class, we refer to that as a 120-degree bond angle as well. We can also have 4 groups that are attached, and there's 3 different ways that this can occur. We can have 4 atoms with no lone pairs. This results in a 109.5-degree bond angle, and we refer to that as tetrahedral. We have 3 atoms and 1 lone pair. We refer to that as trigonal planar, still a 109.5-degree bond angle, and we call it that because if we get rid of the non-bonding electron group, we don't consider that in the geometry. It looks like a pyramid. And then 2 atoms and 2 lone pairs, we refer to that as angular or bent, with also a 109.5-degree bond angle. Many of you are going to have a VSEPR chart on the back of your periodic table or a VSEPR chart in some way, shape, or form. Many VSEPR charts look different than each other, so the terminology that I may use in this video may be different than the terminology that your professor uses. But it's very, very important to make sure that you know how to fully utilize that chart. And again, you notice the importance of drawing Lewis dot structures correctly. A correct Lewis dot structure will allow you to correctly determine the geometry of the molecule that's listed there. So take your time, work through each of these, and understand the different number of groups. In addition to the ones that we've discussed here, there are a couple of outliers that you may find, probably not in this course, but other courses. You can have steric numbers or group numbers of 5 and 6. Those go beyond a normal octet most of the time, and we don't discuss those in this class, but they are available. I do have videos available that do go through and show that. All right, so if we take a look here, the geometry of more complex molecules can be determined the exact same way we've discussed previously. We just have to look at what surrounds the atom that we are looking at. So for acetylene on the left-hand side here, you see that if we looked at each carbon in acetylene, they both have 2 electron groups. They both have a steric number of 2. And no lone pairs, so that would identify, or both of them would identify as being linear or 180 degrees. And you see that there really is no bend in the chain that's there. When we look at hydrogen peroxide, each oxygen there has 4 groups, or a steric number of 4 that's attached to each oxygen, because each oxygen has 2 bonds and 2 lone pairs that are attached to it. So that means that each oxygen is going to have an angular or bent geometry, and you see that in the structure that I've listed down there below. Hydrogen azide, see, has quite a few different number of electron groups associated with each nitrogen. So the first one there has 3 and the second one has 2. So because there's 2 atoms in a lone pair, the very first one on the left-hand side is considered angular or bent, and the one on the right side, because it has 2 electron groups, a steric number of 2 and no lone pairs, is considered linear. So you see there's a different bend in the chain. So we can look at more complex molecules and their geometries. We just have to look at the steric number that's surrounding the atom we're looking at, or the atom that's in question. All right? So that being said, what I'd like to do is go back, look at the Lewis structures. We've already drawn these Lewis structures before. They are from a previous slide, so you can go back and redraw them now. I'll probably do that here in the video here in just a moment. And then what we're going to do is apply the steps and determine the geometry for each of these that are listed. So take a moment, try that on your own, and then we'll come back and discuss it as a group in a moment. Thank you. All right, so what I'm going to do is I'm going to just briefly draw out these Lewis dot structures, and then we're going to utilize the information we looked at previously to determine the geometry. Again, if you have a geometry sheet handy, it would be very, very helpful with all of this. Something I probably could have done earlier, but I didn't. So you're going to have to suffer with everyone else. Yes, these are makeshift. Yes, these are done relatively quickly. Primarily because I just know the structures. It's the benefits of working in chemistry for, 10 years or so. You kind of get the hang of things. All right. So now what we want to do is we want to apply the steps that we just talked about to determine the geometry of these structures. So the first thing I want to look at here for NCl3 is what is my steric number? That is how many regions of electron density or electron groups are attached to my central atom. Remember that is, I'll just use the term steric number, atoms plus lone pairs on your central atom. So if I look at this very first one here, my steric number is 4 because I have 3 atoms and 1 lone pair that's attached. And again, we can utilize that information. Go to my geometry chart. What I find is that this is going to be trigonal pyramidal, and the bond angle is 109 degrees. It's a set of steps, just like everything else that we've done. pH3 is in a very similar vein here because its steric number is also 4, right? You have 3 atoms that are attached and a lone pair, so the steric number is 4. It's 3 and 1, just like the last one, 3 atoms and 1 lone pair, so it's the same. It's trigonal pyramidal and a bond angle of 109 degrees. Last one down here on the left-hand side, we have a steric number of 4. Right? 4 atoms attached. So it's 4 and 0. So this is tetrahedral. And a bond angle of 109 degrees. It's the same steps we've looked at, all right? I don't know what to tell you. It's a systematic, it's a formulaic process. The more we practice with this, the better we get at it, I'm telling you. This next one here, HCN, has 2 atoms and no lone pairs attached to a central atom. So we have a steric number of 2. It's 2 and 0, so it is linear, and it is 180 degrees. Same with this one down here, CO2. Remember, it's the number of atoms, not the number of bonds. So for this one down here, my steric number is still 2. It's 2 and 0, 2 atoms and no lone pairs, linear, 180 degrees. Last one down here, H2O, steric number, right? It's 4 because we have 2 atoms and 2 lone pairs that are attached. It is a 2 and 2 situation, meaning we have 2 atoms and 2 lone pairs. So if I go and look at my chart, it is bent, still 109 degrees. Okay? So again, drawing the Lewis dot structure is hugely important when going through and determining the geometry of these molecules because everything has to be bonded correctly and you have to have the correct number of lone pairs in order to ensure that you've gone through and done all of this correctly. All right. So the next step for this is taking this concept of geometry and figuring out if a molecule is what is called polar or nonpolar. And that has to do with the distribution of electrons that you find around the atom in and of itself. All right. We'll discuss that here in just a moment and then go from there. All right, so we're going to take a little bit of a step back and look at things from a little bit of a different perspective here in terms of not only differentiating ionic and covalent bonds, but being able to differentiate between different types of covalent bonds as well. And this will become more relevant when we go through and look at these numbers in a little more detail. But we're going to look at a chemical concept that is known as electronegativity. And the concept of electronegativity is its attraction, or the attraction an atom has for a shared pair of electrons. Now, it doesn't seem like it means a whole lot at this point in time, but the higher the numerical value here, the more attracted a shared pair of electrons is going to be to that atom. So, for example, if I look at carbon and fluorine, and let's say we have a bond between carbon and fluorine, the pair of electrons are going to be much more attracted to fluorine than that of carbon because fluorine has a higher electronegativity value. We can actually get so far apart in electronegativity values that we can say that the electrons are not shared, but rather donated. And again, it's going to be based off of the difference in the values of electronegativity. So these values play a pretty important role in determining a variety of different physical and chemical concepts. Now, again, when we look at electronegativity, we're looking at two different atoms that are in a chemical bond. And the differences of electronegativity of the two atoms within that chemical bond tell us about what is called bond polarity. This is the inequality of the sharing of electrons between two atoms. And there's two types of bonds that we're going to be focusing on, specifically with covalent bonding and the sharing of electrons. The first is what is called non-polar covalent bonding. And that just means that the electrons are shared evenly between the two atoms that are in that particular bond. This results in a very low difference in electronegativity. A polar covalent bond is an unequal sharing of electrons. You'd have a large difference in electronegativity. Polar just means that one side of the bond has a greater negative charge than the opposite side. So you can imagine that something with a large difference in electronegativity results in a fairly uneven sharing of those electrons due to the higher difference in electronegativity. So let's look at a couple of examples here. The first is a hydrogen-hydrogen bond. And if we go back and look at the electronegativity chart, we find that there is no difference in electronegativity between the two atoms that are present in this bond. So what that means is that the electrons are directly in between the two hydrogen atoms here. There's symmetrical distribution of those electrons, so therefore it's a nonpolar covalent bond. The electrical distribution is symmetrical. If I look at, for example, hydrogen and chlorine, there's a large difference in electronegativity between the two atoms in the bond. Chlorine has a significantly higher electronegativity value than that of hydrogen, and so this results in that pair of electrons being much closer to chlorine than that of hydrogen. And you can see this in the examples shown on the right-hand side here. We have a little bit of a graphic that shows the distribution of electrical charge. The electron density is displaced towards the chlorine atom because it's greater electronegativity. That is, the attraction of electrons in the pair that's being shared between the hydrogen and chlorine is much closer to chlorine than that of hydrogen. So you end up with a polar covalent bond because the electron distribution is not symmetrical. And because chlorine has the higher electronegativity, it has the electrons much closer to it than that of hydrogen. So that makes chlorine have a slight negative charge in the bond when compared to that of hydrogen. Remember that electrons are negatively charged. And so that shared pair of electrons being closer to that of chlorine means that chlorine has a relative negative charge. And by definition, if chlorine is more negative, that makes hydrogen more positive. You see a little, almost looks like an 8 that's just unfinished there. That represents a lowercase delta symbol, which just refers to the concept of change. So we place the relative negative charge on the atom within the bond that has the greater electronegativity, and the positive charge goes on the atom within the bond that has a lower electronegativity. Now, a lot of times we don't just draw positive and negative charges with this, but what we do is we draw an arrow, and the arrow points towards the higher electronegativity. Now, there's no need for this in nonpolar bonds because the electron distribution within the bond is even, right? So there would be no arrow pointing towards the atom of higher electronegativity because in nonpolar covalent bonds, the electronegativities are very similar. And you'll find this will be quite useful a little bit later on. So what I'd like us to do here is I'd like us to draw the partial positive and negative charges on the following pairs of atoms, and then show which way the arrow is going to point based on the electronegativity values that are given in the electronegativity chart that has been provided to you previously. Take a few moments and we'll go over this together. All right, so let's go ahead and write out the partial positive and negative charges of the following pairs of atoms and write out which way the arrow will point. So let's just draw each of these bonds. So when we look at bromine versus carbon, you find that bromine has a higher electronegativity value than that of carbon. So what that means is that the partial negative charge is going to go on bromine and the partial positive charge is going to go on carbon. The arrow points towards higher electronegativity. I'm going to go ahead and change color for this. So what that means is that we're going to point this direction towards the higher electronegativity. Oxygen and chlorine actually both have an electronegativity value of 3.5. So because they have the same electronegativity value, they share those electrons evenly. There's not one side that's going to have electrons closer to it than another, so there's no need for a dipole arrow, and in addition to that, there's no need for the positive and negative charges. For sulfur and fluorine, fluorine has the higher electronegativity value, so we give it that relative negative charge, the sulfur the relative positive charge, and again, we draw the dipole arrow. We're just going to point it towards the atom in the bond with higher electronegativity. Okay? So again, you can utilize the chart. The electronegativity chart is not something you need to memorize. It's something you just need to learn how to practice with. Okay? Let's move on and we will go from there. So the next thing we're going to analyze is based off of the electronegativity values, we can also classify types of bonds. And I know that we've spent a lot of time classifying bonds as either just ionic or covalent. And that is based off of whether something is metal plus nonmetal or two nonmetals that are bonded together. So to find the difference between the two electronegativity values and classify based on the system on the right-hand side here, so we see we have some electronegativity differences. So anything between 0 and 0.4 in terms of differences is considered nonpolar covalent. Anything that is 1.5 to 0.4 is considered polar covalent based on this chart. Ionic or polar covalent between 1.5 and 2.0, and again, that depends on metal plus nonmetal or two nonmetals, and then ionic 2.0 or higher. I'm actually going to make this chart a little bit more simplistic. So for people who are in my class, it might be a little bit different than professors who are in a little bit different class, but this just makes things a whole lot easier. Anything bonded to itself will be nonpolar covalent. Two nonmetals that are bonded that have different electronegativity values are polar covalent, and metals and nonmetals are going to be ionically bonded. So it simplifies this process just a little bit. Polarity very much is a continuum. That is, it's not really just buckets that we dump these things in, kind of like what we're doing here, but rather it is a continuum. Some bonds are slightly polar, some are more polar than others, some are more non-polar than others. It's very difficult to sit here and say what exactly is a polar bond versus what is a non-polar bond. So I'm just trying to simplify it for your sake. Anything that is bonded to itself, non-polar covalent. Two nonmetals that are bonded that do not have the same electronegativity value, we'll call them polar covalent. And metals plus nonmetals we'll call ionically bonded. But again, I wanted to put this chart here because I know different professors use things a little bit differently, and I know other people are going to be utilizing this video, so keep those things in mind. Everybody does things just a little bit differently. So now what I want us to take a look at is to be able to classify these based off of whether they are ionic, polar covalent, non-polar covalent, based off of their electronegativity values, or based on what we just discussed. So take a moment, run through these, and we'll practice in just a moment. All right, so utilizing the concepts that we've just discussed here, let's figure out if these are ionic, polar covalent, or non-polar covalent. So first thing I'm going to look at here is Ca and Cl. That is a metal plus a nonmetal, and we went ahead and said that that is going to be an ionic compound. Now, I feel quite remiss that I forgot to mention this, but one of the rules that I'm going to go through with you is carbon and hydrogen, and I failed to mention that. Carbon and hydrogen do have two different electronegativity values. They're not the same atom, but most people, most chemists, consider carbon and hydrogen to be a non-polar covalent bond. And that ends up saving us a lot of time a bit later on when we look at molecular polarity. So I do feel bad for forgetting to mention this, but this is a non-polar covalent bond by most chemists' definition. So I'm going to define it as a non-polar covalent bond as well. Fluorine and iodine have differences in electronegativity. This is a polar covalent bond, two oxygens, same electronegativity, non-polar covalent. So I think the big take home here, and again, I feel bad for forgetting to mention this, but carbon and hydrogen most of the time, most chemists are going to consider that to be a non-polar bond, because what you find is that most chemicals that just contain carbon and hydrogen in it are going to be considered non-polar chemicals. So the next step with this is taking the polarity of the individual bonds within a molecule and determining, is the entire molecule itself a polar or non-polar molecule? That's something we'll discuss here in just a moment. All right, so we only have a few more things left to wrap up for this particular video. The first one is going to be molecular polarity, and the last thing we're going to look at is our covalent bonding nomenclature. So I want to take the concepts that we last looked at and use bond polarity to actually solve for molecular polarity. And it's important because it determines the relative strength of forces in between different molecules within the same material. So like I said, we'll discuss that a little bit later on. But for now, let's discuss the concept of molecular polarity. Polar molecules show asymmetrical electrical charge, whereas nonpolar molecules show symmetrical electrical charge, meaning that the distribution of electrons is even. It can be a bit tricky to determine this. There are a few tips and tricks to going through and determining this, but how we go through and we follow this is very similar to what we've done previously. First step is to draw the correct Lewis structure. Second, determine the correct geometry and draw accordingly. 3, draw your dipole arrows for each bond in the molecule. So that's the additional step here, is look at the dipole arrows that exist within the molecule. And then the next step is to find the situation that best fits the molecule. Nonpolar molecules will have either all nonpolar bonds, so we wouldn't draw any dipole arrows, or polar bonds that cancel one another. Polar molecules are going to have unbalanced polar bonds or lone pairs on your central atom. Now, I know that that is going to be different for each class, because this class is a fairly simplistic representation of molecular geometry, polarity, and intermolecular forces. Lone pair on your central atom are going to be an indication of polarity. So a couple different ways we can go through and do this. So a couple of examples here. I've put 2 different molecules here for us to determine the molecular polarity for. The first one here is CO2. And notice I draw the dipole arrows that are pointing away from carbon. That is because oxygen has a greater electronegativity than carbon does. And there are 2 carbon-oxygen bonds that are here. Okay, so notice that we have 2 dipole arrows. They are pointing directly opposite of one another. So these would cancel one another. Another way to look at this, and this has been quite successful for some of my students, is to think of these as forces that act upon the molecule. So in that carbon dioxide molecule, you have a force that's pulling to the left, and you have a force that's pulling to the right, and they're pulling exactly opposite of one another. Well, that molecule is not going to move. It's going to be completely stationary, and if that molecule remains stationary, you can consider it to be a non-polar molecule. Consider the H2O that's listed down there below as well. You have 2 dipole arrows, both pointing towards oxygen, but notice that they're not exactly opposite of one another. They cancel each other left to right, but both of them are pointing upwards, so the molecule would still be considered polar because the dipole arrows don't 100% cancel each other. If you had one pointing up and one pointing slightly down, they would cancel each other, but both are pointing up. This means that their dipole arrows don't cancel, so it is considered a polar molecule. This is one of those things that's just going to take a lot of practice in order to get really, really good at. Look at HCN, for example. We've drawn 2 dipole arrows here, one between hydrogen and carbon and one between carbon and nitrogen. The carbon-nitrogen dipole arrow points to the right, and the hydrogen-carbon dipole arrow points to the right as well. Now, if you were to follow my rules, you actually wouldn't draw a dipole arrow with hydrogen and carbon because we consider that a non-polar bond. But regardless, you have 2 dipole arrows that point to the right. Neither of them cancel each other out, so this molecule is also considered polar. So again, it really focuses in on following the rules, determining the geometry, and figuring out, do my dipole arrows cancel or do they not cancel? There's other ways to determine molecular polarity. I think I have a few hints on the next slide, but for right now, let's go through and practice with this together. Let's determine the Lewis structure, geometry, and polarity for the following molecules. Take a few moments, we'll do this together, and then we'll come back and wrap things up because I've got one more thing I need to discuss. All right, so I've zoomed in a little bit for each of these because I want to draw these Lewis dot structures out and kind of go underneath to figure out the rest of this. So bear with me as I go through and relatively quickly draw out these Lewis structures. But again, kind of the benefit of knowing what you're doing makes this a lot easier. And then what we'll do is we will go through and, not do that. There we go. One of these days I'll learn how to work with my iPad, but for the time being, just bear with me as you're going to have to suffer through the immense pain of watching me try to get all this figured out. Oh goodness, there's plenty more left. Okay. PF3, I can do that. SCl2. and CH3Cl. Just making sure I have enough room here. Okay. So now let's go back and determine the geometries for each of these. Okay. So for the first one here, we have a steric number of 4 and 2 lone pair. So that is going to be bent. The next one here, we have a steric number of 2 and no lone pair. So that is linear. For the next one over, we have a steric number of 4, again, atoms plus lone pair. We have a single lone pair, so that is going to be trigonal pyramidal. Next one over, steric number of 4. I know I'm working through it pretty quickly, but again, you practicing is what's going to make this better. So keep working on it, keep practicing, keep getting better. And then the last one here, we have a steric number of 4. No lone pair, so that is tetrahedral. Okay, so now the next thing I need to do is I'm going to go through and I'm going to draw some dipole arrows on these. And our job here is to determine, do those dipole arrows cancel? Do they not cancel? And then is this molecule polar or non-polar? Oh, I didn't even do this first one here. Silly, what a silly goose I am. Steric number of 4, no lone pair, is tetrahedral. Okay. So now we draw our dipole arrows. First thing I notice here is that each bond is going to be needing a dipole arrow if it is a polar covalent bond. If it's non-polar covalent, we're not going to draw it out. So the first one here is CH4. Remember that carbon and hydrogen are considered non-polar bonds. So this has all non-polar bonds. There's no dipole arrows, so this means that this entire molecule is non-polar. Next one here. Our dipole arrows, remember they point towards the atom of higher electronegativity, so we're going to point these both up towards the oxygen. Okay, and then again, we have to ask ourselves, do these dipole arrows cancel? And the answer is no. And again, you can also utilize the concept of we have lone pair on our central atom. So this molecule is polar. CO2. Dipole arrows are going to point outwards towards the oxygen due to oxygen having a higher electronegativity than that of carbon. Again, ask yourself, do these dipole arrows cancel? Yes, they do. So this is a non-polar molecule. So even though it has polar bonds, it is a non-polar molecule because those dipole arrows cancel each other out. PF3. Our dipole arrows are going to point towards the atom in the bond with higher electronegativity. So between each phosphorus and fluorine, fluorine will have the higher electronegativity, so arrows will point outwards. Notice that all 3 of those dipole arrows do not cancel. Okay, the one up here at the top, there's nothing in the bottom that goes through and cancels with that. In addition, we also have that single lone pair on your central atom is a polar molecule. HCl2. Same thing here. We're going to point our bonds or our arrows to the atoms in the bond with higher electronegativity. Those will not cancel. So again, I even rewrite these in the correct geometry to get a better idea of whether they'll cancel or not. We also have lone pair on our central atom, so this is polar. The reason why I draw these this way, and something you may want to do as well, is that when you go through and draw these out, you may want to go through and redraw them. And the reason I do that, let me show you why, is because if you were to draw this, let's say you were to draw this as if you thought it might be linear, and you were to go through and draw your dipole arrows just like what we just discussed, you might think that because you think this is linear, those arrows would cancel each other out. And we know that that is not the case. Because this is bent, the molecule's shape looks a little bit different than what it would if it were linear. So you need to take that into consideration when you go through and draw these out, is that if you didn't draw it in the appropriate shape, you may want to redraw it because that's going to help you determine the polarity of the molecule itself. Last one here is CH3Cl. Remember that carbon and hydrogen bonds are considered nonpolar. We have a carbon-chlorine bond here. The dipole arrow points to the right. There's nothing that's counteracting it. There's nothing that's canceling it out. So this molecule is also polar. So It is tricky, but practice is going to make this good. So draw those Lewis dot structures correctly, determine the geometries, rewrite the structure in terms of the correct geometry if you need to, and then determine the polarity based on the rules that we've gone through and previously discussed. Okay, let's move on. I wanted to provide just a couple of other hints into terms of determining the molecular polarity, because sometimes all of these steps can be a little bit difficult, and I like to provide shortcuts. The shortcuts are going to differ depending upon the professor and depending upon the class, but I found that for the most part, these shortcuts tend to make life a whole lot easier for individuals. So some polarity hints. Any molecule completely surrounded by the same atom is a nonpolar molecule, provided that there are no lone pair on your central atom. So CH4, for example, CCl4. All of these have the same atom surrounding the central atom and have no lone pairs on that central atom. So those will be nonpolar molecules always. Any molecule with a lone pair on your central atom is polar. Again, different classes will differ than this. If you have expanded octets, sometimes that rule does not necessarily apply. So you can't always utilize that rule, but for me and for my class, you absolutely can. Any molecule with different atoms attached to the central atom is considered polar. So I used the previous example of CH3Cl. The carbon atom in the central atom had 3 hydrogens attached and 1 chlorine. Those are all different, so the molecule in and of itself will be polar. So these tips and tricks are actually quite helpful because it prevents you from having to do a ton of extra work to figure out the polarity of the molecule. And again, like I said, these rules will differ depending upon who your professor is and how the class runs. Okay, so the last thing I'm going to cover in this particular unit, and I know I've covered a lot of materials already because this is a very heavy unit in terms of the materials that are covered. Practice, practice, practice. The last thing I'm going to discuss here, and this is something that I will actually like to teach with the ionic materials, is naming of these covalent compounds. And we're going to finish up the naming of compounds. So remember, we've used these when we're dealing with stuff that is just non-metals. So remember that nomenclature rules are always based off of what the molecule starts with. In this case, if it starts with non-metal, you're going to follow this set of rules. And it's very easy because we're not dealing with charges. We're not dealing with Roman numerals or anything like that. There's no crossing and dropping. We just focus on prefixes, and those prefixes are based off of the number of atoms that are present. So the best way to do this is to look at kind of the generalized formula for this. It is prefix plus the full name, and then prefix plus the second stem "ide." There's no charges, no cross and drop, and we actually omit the prefix mono on the first name. And if you look at the prefixes on the right-hand side here, you should be familiar with most of them if you've taken any basic geometry class in high school. Mono is 1, di is 2, tri is 3. Tetra is the tricky one because many people want to put quad there. But tetra means 4, and the easiest way to remember this is if you've ever played the game Tetris, which is a very old school game, but I am an old school individual, that the individual, they're called tetrominos, the individual little blocks that actually fall down are made up of 4 blocks each. So tetra means 4, penta means 5, hexa 6, hepta 7, octa 8, nona 9, and deca 10. So we use these prefixes again based off of the number of atoms that are present. So look at the examples on the right-hand side here. CO, carbon monoxide. That goes back to that last rule. We omit mono on the first name if it just has 1. Notice there's no reducing either. O2, F2, dioxygen, difluoride. We don't reduce them here. So if we're dealing with something that is, I refer to this as type 3, or something that is covalently bonded, we only focus on the prefixes. We do not reduce any of these as we work through them. So we have the following compounds. They're containing nitrogen and oxygen. Let's go through and name them. Take a few moments with this and we will name them together here in just a moment, and then we'll be close to being done. So we're going to use prefixes for these, and the reason I know we're going to use prefixes is that all of these start with a non-metal. Okay, so let's look at what we have here and use the prefixes and go from there. So NO, we know that this is going to be some form, well, all these are going to be some form of nitrogen. And it's going to have oxide. We don't use mono for the first prefix here, but we would for the second. So this is nitrogen monoxide. NO2, again, nitrogen. 2 oxygens here. The prefix for 2 is di, so this is nitrogen dioxide. N2, We use prefixes for the first one if it's not mono, so this is dinitrogen, monoxide, N2O3, dinitrogen, trioxide, N2O4, again, no reduction here, dinitrogen, tetra, oxide. Sometimes we drop the O there, it just depends, but as long as you're following these steps, you should be fine. Remember, no mono on the first, mono on the second for sure. So anything with the number of atoms on the second part, you always include the prefix. You include the prefix with the first part. You just don't include mono if it's just one. Easy way to remember that, it's called carbon dioxide, not monocarbon dioxide. All right? Last one here, we're going to write out the formulas for the following compounds. So we're going to utilize the prefixes we just discussed. We're just going to kind of figure it out using different molecules this time. And you should be able to work forwards and backwards as you do this as well. So we'll practice with some of the opposites here probably in the next video. So write out the formulas for the following compounds. Well, let's do that. So CO, each has a prefix of 1. So this is carbon. Remember, we don't use the mono prefix on the very first one. O is oxide. There's just one, so this is carbon monoxide. HF, again, one atom of each in the molecule, so this is hydrogen. Monofluoride. Okay, for those of you who are familiar with acid nomenclature, this is going to be written a little bit differently. We don't do acid nomenclature here in 1030. SO2, S is sulfur. O2, dioxide. P4O10, so 4 is tetra. P is phosphorus. We have oxygen here. O is 10, so this is decaoxide. So again, sometimes that O is left off there. Doesn't really matter for me one way or another, as long as you get the prefixes down. So that being said, there's a lot that's going on here. We've covered a lot of material: Lewis structures, covalent bonding, geometry, polarity, and naming of compounds. Again, take this information here, especially for the naming. Make sure you incorporate that with the naming materials we looked at previously, because mixed practice is very, very important. The first thing you should do when you're dealing with mixed nomenclature practice is make sure that you understand how to name things correctly. Make sure that you know what the chemical compound is starting with. That tells you what rules you use. These rules with the prefixes, you're only doing prefixes if it starts with a non-metal. That is, it starts with something that is to the right of the stair step on the periodic table or hydrogen. Everything else, charges and cross and drop. So that being said, that is a brief overview of all the material here in chapter number 5. I know it's a lot. We're going to kind of skip ahead and move forward to, I believe, chapter number 7/9 is the next one we're going to look at. I'll have to remember off the top of my head. I honestly don't remember. But if you've liked the video, if you thought this was helpful, leave a like, subscribe if you're interested in more chemistry content. Thank you so much for watching. If you have any questions, feel free to reach out. I'll be happy to help you in any way, shape, or form. Have a fantastic day, and we'll see you soon on the next video. Bye, everybody.